Okay, welcome back, everybody. It's my great pleasure to introduce Kim Brannan to you. I've known Kim for probably more years than he would care to mention. Always a pleasure meeting with you, Kim. I had the pleasure of visiting the DTU Wind site in Roskilde just before.
Paul, you muted yourself.
I must have double clicked. Sorry about that. So I was just saying I've known Kim for many years, and last year I had the great pleasure of visiting him and his colleagues in Roskilde. An amazing site. I always used to know it as the Risu National Labs, and then it became part of DTU a number of years back. For me, it's always sort of led wind energy research from a university perspective anywhere in the world. So it's a great pleasure to have you here today, Kim. Without further ado, I'll let you share your screen, and you're already unmuted. And please start whenever you feel comfortable.
Thank you, Paul. It's been a pleasure to be invited to this event. I hope you see this slide now. And does it move?
Yes, it does.
Super. Thank you. Yes, so today I would be talking about some of the work we do in my section. We have some projects that has recently ended, but also current project running. And some of the things we work with is using digital twins, and I would like to talk about some of the opportunities we see with that, and also about advanced condition monitoring using thermal cameras and drones. If you do not know DTU Wind Energy, I can say that we are a world-leading department for wind energy as part of the Technical University of Denmark. And we work with almost all aspects of wind energy, from looking into materials with X-ray tomography and to using satellites and creating the global wind atlas for the whole Earth, where I can say if you look at Ireland, there's really amazing wind resources around Ireland. But today, as I said, I will be talking a bit about digital twins and opportunities with that, inspection using thermal cameras, and how to monitor and predict damage growth in focusing on wind turbine blades. And I have a lot of contribution from colleagues to these, and most of the material here is you can find more details with these papers on the list there, if you are interested to go deeper. So what is a digital twin? I think there's a lot of different definitions and thoughts of what digital twins are. And NASA was some of the first that started to talk about this, and it has also mainly been used in aerospace and more recently in car industry. But I personally like the definition to the right from Bolton and colleagues. A digital twin is a dynamic virtual representation of a physical object or system across its lifetime, using real-time data to enable understanding, learning, and reasoning. So digital twins are meant to help us to take decisions, to understand things, and be more wise in how we deal with structures. I want to say a few words about a big project we have running currently. It's called Reliablade. It has a lot of industry partners, but it's also special in that sense that it's two national projects, a Danish-funded national project and a German-funded project. And we, from the start, thought of combining these two national projects before we applied for the funding to one bigger project. And we succeeded both in getting funding, and now we are running this project. And it's about improving the blade reliability through the application of the digital twins. over the entire life cycle of a wind turbine blade. And I want to show you the vision of why we made this project and what we intend to do with it. It's very ambitious vision, and we will not reach everything within the project. So this is a more long-term vision, you could say. So imagine that in the future, when a blade comes out of the blade factory, it's not just the physical blade that comes out, but it also comes with a digital twin, a digital representation of that unique blades. We know blades are currently mainly handmade. They're not perfect, I must say. And we use scanning technologies in this project to scan the blade so we can update a numerical model of the blade so it actually represents what is both inside the blade with different defects. We use ultrasound, geography, different methods to look inside the blade, but also to scan the surface geometry so we can have the real surface geometry of the digital twin. In that sense, we have a representation of the blade when it leaves the factory, so to speak. In the project, we are not, even though we have industry partners like Vestas, Siemens Gamesa, and wind power, we are not using their blades, but we are designing and manufacturing blades in the project. So it's open design. We work with a small blade at DTU, 12.6 meter blade, EVIS, Fraunhofer manufacture and design a bigger blade, 31 meter blade. So it makes it possible that all data around these blades are available to the consortium. Well, back to the definition of the digital twin here. So we also embed sensors in the blades. We look at different sensor system, measuring system, so we can detect damage as they grow, and with that update the digital twin so it always represents the true state of the physical blade. And the opportunity or the uses case with the digital twin, there are many. You can imagine many different, but what we focus on in this project is predictive maintenance. So to understand what is happening in the blade, be able to predict how these damages will grow, and then take decisions on what to do with the blade. If it should be repaired, you can then, with the digital twin, simulate different repair methods and take decision on which one will be the best for the blade. You can also use the digital twin to figure out how you should operate the wind turbine if there's a damage, so you will not make this damage grow further before it can be repaired. So there's a lot of opportunities with digital twins. This is kind of illustrating our vision in this project. We are not operating wind turbines. We are running or testing the blades in our blade test facility. So we are doing it in a controlled environment. So back to using thermal cameras, because thermal cameras are great to monitor damage and defects under the surface that cannot be seen by the naked eye. So one way of using thermal cameras is to put a heat source, heat up the structure, and then make the radiation of the heat from the structure that will reveal what is underneath the surface. I will show you an example of that. But another way is, of course, that damage, things that happen inside the blade generate heat. That can also be seen by thermal cameras. A heat source can be the sun, so this is definitely possible to use, and many drone companies use this to inspect blades at sunset. So when the sun go down, then they can detect the damages by looking at the difference in radiation. So this is an example of a blade structure with a pure poor adhesive bonds, where it has been exposed to heat, and then the thermal camera will show clearly that there are some areas where the bonding is good, and some areas where it's bad. So that thermal cameras can be used for that. Another example of a fatigue test we do in our facility, where we have instrumented this small blade heavily with a lot of different sensor systems. But I will not talk much about that today, but more that we also use thermal cameras to monitor what happens to the blade during this test. So we have designed the blades with, or get the blade manufactured with a number of defects on purpose. It's a small 14.3 meter blade. There are 4 wrinkles inserted into the spar cap. There are trailing edge delaminations, and there are also some sandwich skin core debondings, and there's also shear web spar cap debond inside the blade. So the illustration here shows how these delaminations are made by casting resin pockets inserts that are put into the blade. And then we test the blade and see what's happening. And this picture show these 4 delaminations. The green here show how they were originally, and then they start growing, and we have marked at different times how much it has grown. And one of them is painted. There's a white paint with a speckle pattern because we use a measuring system called digital image correlation. And it also show that, I mean, one of the wrinkles, you cannot see what's happening. The others, where they're not no paint, you can easily see what's happening. And not, of course, the painted is more representative as a real turbine blade. But the interesting part is that you clearly see all 4 defects with a thermal camera. And actually, it turned out that the one under the paint was the most critical. It was the one that grew more and actually caused the blade to fail. And it's also seen that it's heat up more. I mean, there's more thermal energy coming from this wrinkle. Another here where we have made a crack or into the trailing edge on purpose, and then a crack is growing from this. So picture A, you can say the blade is not, it's a standstill. You see nothing. And then shortly after you start to with the fatigue test, the cracks show up clearly as a thermal image, and as it start growing, you will see heat coming more from which direction it grows in, and it's easy to see from quite a big distance with a thermal camera. So it's easily to employ into drone applications, and with a naked eye, it's not easy to see it. So we have worked with developing methods to automatically detect these defects and then map them. So there's made some calculation. I made an algorithm that automatically say, okay, this is blade. Here we have a defect, detect it, make the outer shape of it, and make a digital representation of how it looks, so it can be embedded into a numerical model of the blade. So with that, with the blade model and the defects, so we're coming back to the digital twin idea here, that we are able to detect the damage and update a numerical model with the damage. so that we can do fatigue calculation, do different kind of calculations to see how critical is that damage, how will it grow depending on the loading. So a few colleagues of mine have developed this method called fast teak, because of course doing these calculations can be quite numerical heavy. So this method is done to speed up this effect. Here's an example of a trailing edge damage, and this method can then be used to with a non-linear fine element analysis, which is normally needed in these cases to make predictions of what will happen with loading history. And so this is part of coming to this idea with having a digital twin of a blade. My last slide here is that we have worked with drone applications. This is not with thermal cameras, but it's with a normal camera, where we are work with artificial intelligence methods to detect. You can train the system to detect different incidents. Here's vortex generators and a lightning receptor, but it can be anything, also cracks from thermal cameras, and make a system so you can, with drones or other devices, can make an automatic condition monitoring system for wind turbine blades. With that, I will end my presentation, and you're welcome to contact me if you need more information or have ideas of cooperation, and I will also be part of the last session so we can take part of the discussion.
That's fantastic, Kim. Great to see the developments on the digital twin. You've made real progress. It's a lot further down the line than I expected. It's not a, and that's a compliment. Those algorithms and the computational aspects are, and linking that into the material science, which what you're doing is fantastic to see. I hope we get some nice discussion on this later. Just as a bit of procedural things, I think folk are still maybe struggling to post things in the chat or even see the chat. So I've been advised that if you leave the session and rejoin, then you should be available. However, we also have the backup, and that is this: can raise your hand and I will find you at the end. So we will get that discussion going, whether text-based in the chat or actually verbally by raising your hand. Thanks, Kim. If you can, you stop sharing your screen, that's great. And with that, I'll introduce our next speaker, which is Chris Harrington from Hexcel. And Hexcel are obviously one of the major material suppliers which end up in wind turbine blades. The floor is all yours, Chris. If you can share your screen, that would be great.
Yeah, hi, Paul. It's just grayed out for me. I'm going to leave and rejoin as you suggested and see if that fixes it. Sorry.
Yeah, that's no problem. We can do that. We've always got the time at the end to catch up with things in the discussion and answer session. I think you're back in, Chris.
Yes, hello again. Sorry about that.
That's all right.
No, I'm still grayed out from sharing. Sorry, that's changed in the last 20 minutes.
Oh, I wonder if our support team can advise you on that. Are you actually in the PowerPoint application?
I'm not even sharing yet. I'm still in Teams, and I'm grayed out for sharing. It says only organisers and presenters can share.
Okay, we'll let our back room.
I'm live.
Chris, you should be good to go there now, and
perfect.
Paul, you should be the same now.
Okay, so do people see my PowerPoint?
Not yet. It's cut. No, not yet. You can see the button now, can you, Chris?
Yeah, I'll do the Teams thing and try it again.
Okay.
Okay, that's looking better from my side.
It's looking great from our side as well. Just check you can advance the slide and then you'll be good to go. Perfect.
Yeah, okay.
The floor's all yours, Chris. Thank you.
What would these events be without some technical challenges to hurdle over?
Oh, we're some of us are engineers as well. We have to solve these problems.
So I would also like to extend my thanks to ICOMP and to Paul for inviting us to talk today. This will be a little bit of a materials supplier view on things. I've tried to make it pertinent to what are the benefits and why would you be interested in the technology. But I'm going to talk to you about paint-ready surfaces derived from prepregs and the technology behind that. So I'm Chris Harrington, and some of you may recognise the root of that name. I am indeed of Irish heritage from the Harringtons down in County Cork in Castletownbere. And I work at the moment for Hexcel. I've been here for over 20 years. And I work in Duxford, which is near Cambridge. And we have a long and proud history in Duxford with composite materials. I have a little advert there for Aerolite glue. That was from 1937, which was actually 3 years after the site in Duxford started its work on synthetic chemicals and composite materials. So we're 87 years into our composite innovation experience here. And we have a shiny new building, which is shown bottom right. We call that our Innovation Centre. And that opened about 5 years ago. And we have 50 researchers who are focusing on research, development, and the characterization of thermosetting materials for composites. And those are all of the formats you would expect. So prepregs, direct molding compounds, adhesives, and we're going to talk about surface finishing materials today. So the presentation, you're going to expect me to talk to you about what a wind blade is and how it's constructed, and then why surfaces are important, and how Hexcel technology maybe offers some scope for cost reduction and innovation at the same time. There's the tear sheet from the Hexcel website on the right there. I'll leave you to enjoy that on our website offline if you want to. And that gives me a minute just to talk to you about Hexcel's innovation philosophy. So it's built on 3 legs. So the first is the innovation and the problem solving that we do ourselves. And I told you about the Innovation Centre in Duxford in the UK, but we have centres of excellence around the world for honeycomb, for carbon fibre, for weaving, and for other product development streams. And then we complement that with acquisitions of adjacent technologies that grow our portfolio. And 4 examples here, you've got electromagnetic shielding modification with ARC, 3D manufacturing or additive manufacturing with Oxford Performance Materials. Formax gave us non-crimp fabric manufacturing, and Structil in Paris for their industrial adhesives and marine portfolio. And then the third element is kind of some of the topics that we've hit on in the earlier talks. So kitting to make reductions in scrap and make materials easy to handle, reduce the burden of waste. Arkema, we have a strategic package running for thermoplastic carbon fiber tape. We know thermoplastics have been there or thereabouts for a couple of decades. I think now we're getting to the point where there's a serious opportunity for exploitation in primary structures. And then finally, carbon conversions. A few people have talked about end of life and recycling. I think an important element of that is what are you going to do with that recyclate once you've got it? And carbon conversions have a a smart take. They certify the incoming batches of carbon fiber to the outgoing recyclate, so you have some traceability in fiber performance. And also they deliver product formats that are usable in downstream composites processing. So they're an important bridge. So if we look at a blade, and this is what we've seen many times before. If we look top right, there's a large root end which we use to bolt it onto the tower and the generator. There's a structure in the middle so it stays stiff and doesn't flap around. And then there's a shielding aerodynamic structure that goes around that. That's your workhorse. That's what's converting the wind into rotational energy, which we then turn into electric. But all over it, you've got a surface, and you've got to paint that surface. And if you think about a wind blade, you probably think they're all white. If you took a handful of blades and put them next to each other, I think as Harold was saying earlier, they're all slightly different colours of grey to suit their environments, or they might have coloured tips for visibility. So you're going to paint it, and a 60-metre blade, that's a baby. We've already heard several times today about 100-metre blades, but a 60-metre blade has got a surface area of over 300 square metres. That's bigger than a tennis court. So you're going to be dealing with a lot of surface if you're in wind blade production. Okay, I'm going to try and jump out to a video here. So Paul, I don't know if you can confirm that that's now sharing a web interface.
Yeah.
Awesome.
You can see your mouse. And it's playing.
There's no funky 70s music on this. You just have me talking. So wind blades are typically made in two halves. So like a clamshell, and then that they may be cured separately and brought together, or brought together and then infused. So on the left, you've got a standard blade manufacturing technology where a gel coat is laid down into the tool before all of the composite structure goes in. And you've got a representation of one man with a roller applying that. For a very large blade, you're going to have 10, 12, 14 people kind of within the tool doing this. And on the right, you've got what we call Hexcel XF technology, which is a fiber reinforced product being laid down into the tool. So in about the same time or less time, you've got both tools prepared for your composite structure to go in. But the gel coat now has to be gelled, which involves heating the tool up. And there's a lot of thermal inertia there and a lot of energy to do that. And then cooling back down again before you can start laying up your prepreg or your dry fiber on top of it. Whereas with XF technology, you're ready to start that composite layup straight away. So for a model system, you're saving a couple of hours of your in mold time. And we're going to hear that mold time is incredibly important. That's the asset that you're spending a lot of money on, and that's taking up a lot of your footprint. So you want to be manufacturing as many blades as quickly as possible to the highest quality with that tool. So if this moves on, the other advantage is you're avoiding some weight and some cost of materials and disposal. And you may have noticed in the animation that the little gel coat people had been given PPE in case they were exposed to breathing of fumes from the two component gel coats or other materials. So are we back on the PowerPoint?
Yeah, I was muted. Yes, you are.
Yes.
Yeah, perfect. Okay, good. So look, this is a really busy slide, and I don't intend to read through it, but in the blue boxes, I've tried to pull out what's the benefit of switching from this gel coat technology to this composite XF technology. So in terms of the material, you get the chance to avoid some parasitic weight on the blade. It's all composite right to the surface. You haven't got this sheath of gel coat around the edge. You've got a quality improvement in the preparation that you don't have to mix, meter and apply gel coat. And there will inherently be variability with that. A change in the thickness of the gel coat in some part of the blade will affect the overall weight of the blade and the balance of the blade. The reduction in labour is really significant. Even saving 10 minutes, if you've got 14 people in a blade, will massively reduce the overheads. We talked about the potential time saving in moving straight onto layup. Excuse me. Straight onto layup. And health and safety, we've talked a little bit about liquid radial disposal earlier today. There's a point on painting, and this isn't out of tool saving. So once you've got your finished blade that's ready for painting, if it's gel coated, you might have to do some NDT to hunt around and find any defects. And then you need to fix them and prep the surface. The XF technology gives you a direct transparent surface. So you can see if there were any sublayer defects and fix them straight away. And it has a very light preparation. One of the built-in features of a gel coat is you apply a reasonably thick layer, maybe 400 microns, so that you can abrade it quite roughly to get the keyed paint surface ready. Whereas with XF, you just need a wash and a Scotch Brighting, and then you're ready to start the paint process. So that's the concept, but that's all meaningless if you can't actually paint the blade. Excuse me. So here's some work that we did on a demonstrator part. So we would call that an intermediate scale part, and I appreciate it's a lot smaller than some of the components we've heard about. But for us, a 1.2 meter by 60 centimeter part is quite large. And we built the four technologies side by side. And you can see that section A is white, so that's the opaque gel coat that would traditionally be used. And then the grey bar at the top, that's where we've applied a standard paint to the panel. And if we whiz round clock fashion from top right, so from the red box, so that's what you would get in terms of surface finish if you applied a multi-axial fabric straight onto a composite mold and tried to make a wind blade. And the graph at the bottom is trying to show you that that's a bad starting point, which is no surprise. You've got a large pinhole area, so you're going to have to do a lot of rework. And also the pinholes are large, so each of them is going to take a lot of attention to fix. Now, we can use fleeces on the surface of components, and we've done that in composites for decades. And if you put a standard glass fleece onto the surface of the same prepreg, same reinforcement, yes, you see a benefit. Your pinhole area is down and you're reducing the size of your pinholes. But that's still not paintable. You're still going to have a lot of rework, and that's going to take a lot of time to get a good surface finish. Now, the baseline, the performance that you have to match is gel coat. That's the incumbent technology. And you can see that's basically 0-0 on our chart, highlighted with green. Now, XF technology sits almost on top of it. So it's just, there are a few pinholes, and they are tiny, not to be overly scientific about it. So they're of the size that if you've got good equipment and you go looking for them, you can quantify them. But we have experience with several hundred blades being manufactured with this technology, and they don't impact the painting process. They're below the threshold value where they become a problem. So if I conclude, and hopefully I'm not running over time, the needs of your surface for it to be paintable are broken down kind of in 5 main themes. And Hexcel XF technology has been developed, proven and launched to hit good quality, because you're controlling the weight, your tolerances, and your distribution in balance in your manufactured blade. And if you saw the layers of the XF going down in the animation, you may be concerned that the overlaps would be a source of defects that needed work. But Hexcel has formulated the resin and the architecture of the system, so actually it's engineered not to give overlap defects. You're reducing the need for labour, and you're reducing the skill level for that labour. So you can have multi-skilled people and less of them. The material is very easy to handle. It's self-adhesive, so you're not putting spray adhesive into the mould. And the grinding preparation for paint is a lot simpler. So you don't have to invest a lot of time in training and kind of utilisation of metrics for that. The material has to be very robust, and we've produced demonstrated components with pre-preg or with infusion, epoxy infusion backing, and the full range of high and low vacuum pressures that you might anticipate you would see. And also, there were some great pictures in the presentation earlier. You saw all of the other materials that are in a wind blade. So there's foams, there's balsa, there's protrusions, there's carbon spar caps. The demonstrators have been done, and the technology is tolerant to all of those as backing materials. We mentioned 2 hits on cycle time saving. So you're avoiding that thermal cycling at the start when it's in the mould, and also you're reducing your prep time. And people often worry about latency and storage when we talk about pre-pregs compared to infusion. So this system has 6 weeks out life at ambient temperature. So if you're building one blade every 24 hours, that's into a domain where you can have a just-in-time or a weekly, bi-weekly delivery and manage stock with no need for investment in refrigeration. So my summary, my takeaway, and I've made it relatively specific to XF for today, is that blade manufacturer or selection of blade manufacturers will be driven by blade cost. And your business case is going to be built on your material cost, your capital expenditure, the labour you need, the footprint and number of tools that you need, and how many blades you're going to send out of the door. And you will significantly shift that business case, and you will win that business case by being innovative and using material differentiation. Wind blade manufacture doesn't have to be commoditized and doesn't have to be driven just by labor costs. I think any country's industry can certainly embrace innovative concepts and change the way and change the business case for blade production. So with that, thank you for your attention. Questions we'll take in the Q&A at the end. But my email is on there, and if people want to reach out to me directly, please feel free.
Thanks, Chris.
Over to you, Paul.
Yeah, thanks. Great to hear about the new XF technology. And I hope you don't mind me just passing a brief comment on the nod to aerolite. I've always thought of Gordon aerolite. It was developed by Norman de Bruyne, I think it's the same way we spell Kevin De Bruyne, but I think he pronounced it De Bruyne, if I'm right. It was the first modern day composite I'm aware of, flax reinforced phenolic.
Yeah, that's absolutely right.
And they developed those artificial resins back in the late 1930s. Fantastic nod there. Moving on, look, I could talk about all day about the history of composites, and I won't bore you with that. It's a forward-looking view today. So our last speaker before we go to the universities is the important one from the Sustainable Energy Authority of Ireland. How many countries actually have a Sustainable Energy Authority? I'm not sure. So it's great that Ireland has one. And over to you, John Buchan, to tell us all about your activities. Could you please share your screen?
Thank you. Just sharing now.
We can see that. Just check that you can advance, okay? And
yes.
The floor is all yours. Thank you.
All right. Excellent. So what I'd be as thank you for the introduction. SEAI is Ireland's energy authority. We deal with renewable energy and energy efficiency and the transition to a low carbon energy society. So I'll be, in my presentation, I'll give an overview of wind energy trends, both nationally and internationally. An insight into the, I suppose, the role of composites research in wind turbine technology development, and an overview of SEAI supports for wind energy RD&D. So on trends, 2020 was a target year for Ireland. Wind energy contributed 36.4% actual output to electricity demand, which is quite, let's say, in national and global terms, that's a very significant contribution. I think we're the leader worldwide for the contribution of onshore wind to electricity demand. Other countries have achieved a higher contribution of wind energy, but that includes both onshore and offshore wind. It was a very large fraction of our total contribution to renewable electricity, over 85% of it. In terms of achieving the target, the 40% target for 2020, we had a near miss when you include statistical normalization, which prevents countries from achieving their target all in the last year. But certainly it still has the growth of wind energy has been a very significant achievement. And its importance, I suppose, not only has wind energy contributed to most of our renewable electricity target, but it also contributed to more than 50% of our total renewable energy across electricity, heat and transport. And on the foot of that success, we have a new 70% target for 2030 that will involve at least 3.5 gigawatts of offshore renewable energy, which was increased to 5 gigawatts in the program for government, and up to 8.2 gigawatts of the total onshore wind capacity. And I suppose the graph below shows what enabled the choice of wind energy, I suppose, as a major contributor to renewable energy and decarbonisation, was really that the technology is very cost effective. And again, SEAI produced a roadmap for in 2011, maybe going somewhat out of date. It shows both the projected onshore wind contributions and projected offshore wind contributions, and we're pretty much on trajectory where we had predicted. Whether we will continue to do so to 2030 remains to be seen. The roadmap could do it being updated to incorporate floating offshore wind also. This is the results of a recent expert survey carried out by IEA Wind Task 26, led by the Lawrence Berkeley National Laboratories in the US. And it shows, I suppose, the projections that of the reduction in the cost of wind energy that have enabled countries to promote it as a leading technology, and countries including Ireland as a leading technology contributing to decarbonisation. That in 2015, LBNL carried out a survey in conjunction with the members of TAS 2025 and produced these graphics for onshore and offshore wind. Let's say the dotted lines are the median results of the survey, and the shaded areas are the span of the contributions. But in all cases since then, the actual cost reductions have outpaced the projections of the experts. So again, LBNL carried out a survey in 2020 and projected the cost reductions to 2050, and there are still significant potentials for cost reductions in both onshore and offshore wind technologies, despite the fact that onshore is quite a mature technology. And certainly floating offshore wind, the graphic there shows that currently its technology cost is at above 22% above that of fixed offshore wind, but that there's significant potential to reduce the cost of floating offshore wind as well. And this graphic, I suppose, illustrates what has been the major contributor to the reduction in the cost of wind energy, and it has been the upscaling of turbines. And a lot of the costs that are associated with wind turbines scale with the number of units. So the size of units of the individual units is important. The number of foundations, your operating and maintenance costs reduce as the unit size increases. And again, from the recent expert survey, it appears that there will be a continued increase in the size of wind turbines. Certainly, there's some sign of it leveling off onshore, primarily due to the transportation difficulties in particular for large wind turbine blades. But offshore transportation isn't such a barrier, and you can see that the technology will continue to scale, and rotor blades in particular will go beyond, well, they're already beyond, our rotor diameters will be beyond 200 meters, but proceed to 250 meters by 2035. So in terms of the opportunities for composites research, really the rotor blades and the development of rotor blade technologies have been what's enabled and been the pacing item for the upscaling of the technology. It is really been developments in the design and the manufacture of wind turbine blades that have determined the pace of upscaling of wind turbines. And the wind turbine blades are much more sophisticated now than they were in their both construction and function than they were in the 1980s. Not only is the aerodynamic design much more sophisticated, but it also its properties as material properties as regards flexing under load also are tailored and again more sophisticated in order to control the loads on the other parts of the wind turbine. In terms of research priorities for wind turbine blades, as the wind turbine blade is such a critical component to the continued scaling and cost reduction of wind turbines and wind energy. One report that you might look to look for what the priorities are for research on composites to contribute to the continued future cost reductions are the an international an IEA Wind report from 2019, which was based on an expert meeting in 2018, which brought experts from all over the world together to identify the research challenges for wind energy to inform the IEA Wind strategy. But it's also a very informative document in terms of being generally informative to wind energy researchers. So the core tables within this report identify key challenges innovations for turbine technology to reduce the levelized cost of energy. I've highlighted with the green arrows the areas that wind turbine blade research may contribute, but in areas, I suppose, blades being optimized for, I suppose, larger rotors being the, let's say, the key determinant or a key determinant of the levelized cost of wind energy. Blades optimized for structure and manufacturing over aerodynamic performance, where aerodynamic add-ons are added on, are installed after the fact to regain lost performance is one area identified. Ultra flexible rotors, innovative materials, extreme load mitigation, and distributed and redundant sensing and controls. Again, implement load sensing within components, and adopting aerospace approaches that include inspection and damage assessment. And I think that these resonate with some of the previous presentations. And again, improved design methods are also identified that would contribute to reducing LCOE, and particularly probabilistic design, improved aeroelastic and component models, and innovative turbine design approaches. And the turbine technology R&D challenges were identified, and I suppose the first grand challenge for turbine technology is a complete understanding of the physics for design and operation of very large scale machines. And it's, I suppose, the first specific R&D activity is validation and verification and of the simulation and design tools is the challenge that's most relevant to composites and wind turbine blades. Again, the report identifies the innovation in manufacturing and industrialization to reduce LCOE, and there are some interesting suggested innovations there. 3D printed molds, 3D printed components, molding automation, finishing automation, low-cost carbon fiber, and other advanced materials. In terms of machine learning, advanced modeling, advanced design optimization, quality control and improvement, I won't go through each of the areas. One particular area that's quite important, particularly given the restrictions on transportation for land-based sites, may be on-site manufacturing or assembly, and certainly segmented blades would solve some of the problems of transportation, but may introduce their own challenges for blade design. And again, there are other challenges also in terms of joining composite materials, and again, on-site manufacture, including 3D printing and robotics. In terms of advanced materials, again, there are significant challenges there, and possibly one of the greatest challenges is recyclability. And certainly in a further slide, I suppose that challenge is now coming to bear on the wind industry as wind turbines reach old age in operations. But again, as other researchers have mentioned, erosion-resistant composite materials, as reducing wind turbine blade manufacturing cycle times, as other, again, presenters have mentioned, and advanced thermoset materials, again, which can be recovered and reused, will be particularly important. And again, automation will have a significant contribution to reducing cost, particularly for the blade, which is the largest single component of the wind turbine. And again, on-site manufacturing has been identified as a key challenge, and there are many areas of research there. And just to mention again, I mentioned the aging wind turbine fleet. This gives the age distribution. This graphic shows the age distribution of wind turbines in the major wind energy regions of Europe, and it can be seen that the fleet is rapidly approaching 20 years or more in age, and this really brings about I suppose the critical decision as to whether to engage in life extension or repowering. And I suppose the remaining useful life assessment is a particular challenge for wind turbine blades and composite materials in general. And Kim, I suppose, mentioned some of the methods that can be applied in the field to assessing the condition of wind turbine blades. Another area of potential a potential contribution for wind composites research is in reblading with improved blade technology, reblading existing turbines to improve their energy yield. A lot of the existing turbines that are aging in the field were designed with old blade technology and, let's say, older out-of-date aerodynamics, and significant improvements can be gained in both weight and performance through using new materials or reblading with redesigned and blades with new materials. But again, this graphic also illustrates the pending problem of disposal of composite blades, which at the moment are not readily disposable or not readily recycled. So the major routes for disposal are incineration and landfill.
John, I really hate to interrupt you. This is such an important topic, particularly I think at the moment of recycling then. But we are running a bit late, so
all right.
Please carry on.
I'll try to finish up as quickly as possible, moving to my last slides. So really, what are SEAI supports for wind energy RD&D? There's the SEAI RD&D scheme. We've just completed our 2020 call for proposals. I haven't got a list of the projects that were successful in that. The next call will be in 2022, but we support all kinds of energy research, and I particularly welcome proposals on wind energy projects. We also manage Ireland's participation in the IEA Wind or D&D technology collaboration program. We have an annual call for participants, and we fund the task fees and travel costs for participants. This gives an overview of the current and completed tasks from IEA Wind. Two tasks that are particularly relevant are Task 45 on recycling of wind turbine blades and Task 46 on blade leading edge erosion. Both of these tasks are new tasks. We have some candidates for participants in both those tasks, but we are interested in, I suppose, expanding the network of people participating in IEA Wind tasks. And the IEA Wind annual report gives details of all of those international research collaborations and the current and new tasks. So thank you very much.
That's great, John. I really thank you for taking the brief so closely to heart. You've really given us some real pointers for where we can focus attention for research into composite materials. And I also want to say, whatever the outcomes of the recent funding opportunity, it's great to see SEAI expand the funding round this time beyond what I've been familiar in recent years. So it's a great opportunity, and looking forward to some great projects being funded to come. So I'm sure there's going to be questions later. We do not want to hold things up any further than they are. Just before we move on to university sector in Ireland, give an overview there. Just want to say we are having ongoing problems with the chat, so we will be doing hands up, the old-fashioned way, hands up, and I'll be pointing to people to voice their questions. Alternatively, you can email me at paul.weaver@ul.ie, and I will go through those and I can read them out. So that's the alternative to the chat. Just email me, paul.weaver@ul.ie. Anyway, with that, we'll move on to the university sector. So it's quick fire presentations from universities that I recognise as working in wind energy sector. Apologies to those I may not have included, but these are the ones that I was aware of, and all universities were part of the Irish Composite Centre funded by Enterprise Ireland anyway, so it made sense to look at the activities that were ongoing there. So the first university to represent themselves is Galway, and from there we have Will Finnegan. Are you there, Will?
Yeah.
Great, if you can share your screen, that would be great.
Yeah. Oh. Can you see that?
Yeah, we're your last slide at the moment, but we can see it.
Yeah, it's on the laptop mode though.
Yes.
So that's still, you're seeing the final slide?
Yeah.
There's always going to be technical problems. Okay, I'll do my best to get in with 5 minutes. So just to start off, the presentation today. My name is William Finnegan. I'm.
Well, hold on though. Well, we can maybe you go out. We can get our next speaker to go, and you can sort that. It'd be nice to see your slides.
Yeah, you're in the. We're actually looking in the wrong view. So if you're reshare again, if you go back out and reshare from the screen which it's presenting to.
Oh, that's very strange. I plugged out my extended screen and everything just to avoid.
No, don't worry. These things happen. I think you just need to go into slideshow mode, don't you?
Yeah, I think it might be still thinking your PC is extended. because it's looking for that screen. We are currently still on your laptop screen.
Okay.
Clodagh here. I was assisted with this earlier on today. If you unclick, oh, I was going to say unclick presenter view, but you probably need that if you want to access your notes.
No, I was going to do it without.
Oh, perfect. If that's the case, you can up at the top there. If you, you have a monitor is automatic there. To the right, to your far right, yeah.
Yeah.
Change that to primary monitor and then share. No joy.
Not happening, no.
Maybe if you're presenting from your from PowerPoint or from your desktop. I found this with Teams.
Yeah, if you present from your desktop
Okay.
as opposed to the application PowerPoint.
Can you see it now?
Perfect.
Success.
Oh, thanks, guys.
Just check you can advance the slide before you start, and then we can. Hey, it's perfect. Go ahead, Will. The floor's yours.
Okay, thanks very much. So apologies for that, and I'll get through this as quickly as possible. So today I'm just going to give you a really quick overview of the work that we've been doing, mainly around composites and, well, renewable energy, but a lot of it is within wind as well. Within NUIG, we also work within the Rhine Institute, MARI, IFORM, and what was formerly ICOMP. So today, broadly speaking, I'm going to talk about the work being performed within the Sustainable and Resilient Structures Research Group. So this is led by Professor Jamie Goggins, who's top left there of the 5 people, and that's me top right. I'm one of the lead researchers within the group. Noel Harrison leads Advanced Composite Manufacturing. Sean Lean and Pat McGarry lead the fatigue and fractures of mechanics or of composites. So within these 3 research areas, we've done a lot of work over the past 10 years, over 100 million funding, a large number of projects, including some Marie Curie projects and SFI industry fellowships to composites and some wind manufacturers as well. So just a brief overview of some of our projects. This is by no means an exhaustive list. But the first one there is the Leap Wind project. So Tomas from Air Composites, who led that, spoke about it earlier, where we developed a novel leading edge protection system aimed at the offshore wind industry. Another one that Tomas touched on earlier was the Crimson project. So we're starting into this. It's a really interesting project where we're helping develop some novel recyclable composite materials and some cutting edge manufacturing solutions for composite foils for a marine energy turbine. So the technologies developed in this project will be applicable to offshore wind as well. We're just at the end of the Mariner 2 project, so we're part of 39 organizations, and effectively within this Horizon 2020 project, ocean renewable energy developers, including offshore wind developers, were provided access to different infrastructures around Europe. So the infrastructure that we were mainly involved in was testing. So we tested some wind components and tidal blades through this Horizon 2020 project. One that's still under review, but the results are imminently, is a project through the Destructive Technologies Fund. It's a 4 million project, and it brings together Noel's team in the Advanced Composite Manufacturing Lab with our Structural Testing Lab. And we're looking at developing composite manufacturing solutions for the next generation of delivery drones. A bit different. It's not wind energy, but the technology is being developed, like 3D printing of composites that was just mentioned in the last presentation, are being developed within this project and are applicable to offshore wind. There's quite a lot of expertise within the university on numerical modeling of composites. So one of the in-house softwares that we've developed is BladeComp. So BladeComp is a composite modeler, and he uses a genetic algorithm to optimize the composite layup within a structure. It's mainly been applied to tidal blades and wind blades so far, and we looked into commercialization. At the moment, there's a beta version that's open source and free to download. Other modeling that has been explored in recent years, and this is an overview, is fatigue modeling of composites. So there was work done looking at tidal turbine blades in particular, and then some work that is more composites in general, looking at multi-axial interfiber fatigue and a puck composites fatigue model, where the numerical model is shown at the bottom of the screen. In connection with the numerical model, there was some work done in recent years by Sean and Pat looking at composite damage and material characterization. So looking at really nanoscale, looking at the micro cracking of composites and validating some of their numerical models by comparing to these test results. On the composite manufacturing side, there's a number of ongoing projects that are funded through Marie Curie, looking at automatic taste placement for advanced composite automation and composites additive manufacturing, so essentially 3D printing of composites. And what we have there is some early work done on parts for the drone project. At the latter years of ICOMP, Noel had some work funded through the ICOMP Centre looking at sensorization of composites, so embedding sensors for structural health monitoring and to limit defects during manufacture. There was also a project that looked at using manufacture to limit the degradation of composites that are being employed in the marine environment. A very high view then of the testing lab. We've tested in recent years, a lot of tidal turbine blades and some wind energy projects. So Leap Wind, Tomas would have shown the picture of this earlier, and that's the in test with the 3 actuators employing a load along the length of a 13-meter blade. And the bottom left-hand corner is again something that was manufactured by Air Composites for orbital marine power. It's that 4-ton tidal blade, and what we've imparted on it there is over a meganewton of a static load, which is the largest recorded load ever put on a tidal blade in the world. And that's the end of my presentation. If you want to get in contact with me with any of the stuff that I talked about there, my email is there, and I can put you in connect with some of the other guys as well. So I'd be happy to answer any questions in the Q&A.
Yeah, that's great, Will. Thank you. Really good overview.
Hope I wasn't too long.
No, you're all fine. We'll move on swiftly on. Limerick is next. I guess being host prerogative, we've got 2 presenters giving detailed aspects of one on folding blades and one on developing carbon fibre from lignin. Before I do that, I just want to say that at Limerick, we've got strong expertise in materials for resisting rain erosion at leading edge. Work has been going on for a number of years, led by Professor Trevor Young. And indeed, we have our own rain erosion rig there as well as structural design and optimization, including moving bits on blades, so morphing aspects. But again, that's not going to be discussed today. The nearest we get to the morphing aspects is the folding blades that Eileen is going to show now. Eileen's internet connection is not great, so she's recorded a presentation. She's a final year PhD student, and we're just going to show the presentation now. Thank you.
Good afternoon, my name is Eileen Bow, and I'm very pleased to share with you an idea which actually brought me to Limerick to work in our research group. Myself, Paul, and Giovanni Succo have been working on this idea for a while, and we think it can benefit the wind energy sector. So I will share during these 5 minutes why we think the idea is valuable and a little bit of how it works. The presentation is entitled The Blade Transportation Challenge. Smaller by folding? So to start, I promise it will be more than a white slide. But I'd like to invite you to imagine the transportation of the blade of the first megawatt wind turbine. Here, I wouldn't like to be the driver, and I have to say that I empathize even more with the driver and the logistic teams after reading a public article from Siemens Gamesa. The article uses as example the installation of a wind farm. To get to the installation site, they had to drive in slopes with gradients up to 32%, sometimes during rain, fog, or snow. The blades were 57 meters long, so almost half of today's largest blades. Finally, the wind farm had 49 wind turbines. So assuming a 3-bladed rotor configuration, this means transporting 147 blades. Unfortunately, this poses not only a logistical challenge, as pointed by the NVGL in 2002. They stated in a public report, very few fundamental barriers have been identified for the cost-effective scaling of current commercial blade designs and manufacturing methods over the size of 80 to 100 meter diameter. The most substantial constraint is transportation costs. In this report, they identify 4 pathways to address the problem: contour blade bending, segmented blades, alternative means of transport, and on-site manufacturing. Our proposal belongs to the first group, control blade bending. The idea is to embed a flexible hinge in the structure of the blade so that the blade can fold. The result is transporting a shorter blade. So what is a flexible hinge? I'll show you through a drinking straw. This is the fun part. Long structures with walls relatively thin when compared to their cross-section, like this drinking straw or a blade, show a characteristic behavior when we bend them. Due to a mechanical phenomenon, after a certain load, the structure bending stiffness becomes very small. At this point, the structure can be folded without the need of a hinge, some sort of a hingeless hinge. So maybe not that impressive for a drinking straw, but if instead we think of a blade and we respect its elastic limits, we could fold, transport, unfold, and install the blade. This would be a new application of flexible hinges, but the concept is already in use for aerospace deployables. One of Paul Former's PhD students, Xavier Lagenal, created a demonstrator of an airfoil section made from glass fiber reinforced polymer. We can see it being tested in the picture. I would like to stress that no additional folding assembly is used. The hinge is created by purposely designing the structure of the blade. Blades are made from composite material, and our study shows that the folding can be tailored through composite material tailoring, so layup selection and material properties. Folding is facilitated using lateral cutout in the folding region. As well as I'd like to offer you a summary of the main strengths and also the challenges of our concept. The key offer is simpler transportation through a smaller blade span, which is applicable to any means of transportation. Compared to segmented blade, this solution represents no or small increase in part count, since the hinge is included in the blade. The implications of this can be reflected in maintenance costs. As well, compared to segmented blades, this concept represents no or small increase in blade mass. Therefore, no additional loads are introduced. I believe also an advantage is the fact that composite materials from which blades are already made are beneficial for the design of flexible hinges. Now, challenges. The first challenge is that the design of the folding region is complex due to the nonlinear mechanics which are behind the functioning of this hingeless folding. We have addressed this until now using the strong expertise of our research group in nonlinear mechanics. A further challenge is the stress concentration that generates in cutouts of the folding region. We plan to address this challenge with tool steering technology, which has proved to be effective for other applications. Our group has strong expertise in tool steering technology, including optimization and manufacturing. With that, I would like to thank you very much for your kind attention. I will be looking forward for the question and answer session, but also feel free to drop me an email at eileen.bowenperez@ul.ie.
Thanks, Eileen. That's great. We move swiftly on to Maurice Collins, who's also from the Bernal Institute at UL. Over to you, Maurice. Can you unmute yourself? We can see your slide, Maurice, but if you can unmute yourself, that's great.
Yeah, sorry about that, Paul. Can you see my slide now?
Yeah, we can see it. Just need to go to slideshow mode.
Yeah, no problem. One sec.
And,
yeah.
And Maurice, if you see my face emerging, I apologise, but that means move on a little bit.
Yeah, okay. No problem. You can see my slides, yeah?
Yeah, just go to the next slide so we can see the advances working.
Yeah, no problem. So greetings from a sunny Limerick, from a sunny University of Limerick. So it was heartening to see a lot of the presentations earlier on. People were talking about materials, the need for sustainable materials, the need for sustainable carbon materials, and how carbon fibers, how they affect carbon emissions, and how we need recyclability. And I guess I'm going to address a lot of those questions with this presentation, which I'll have to go through quickly. So I think we all know that the current situation is that all these materials that we're working with are fossil-based. So be they thermoset or thermoplastic materials, they're all fossil-based materials. The carbon fiber within them are also fossil-based. So they're quite dirty. They lead to climate change, and it's not the way forward. There's also carbon materials are also mined from the ground in places like China, and these contribute to health factors as well, and obviously pollution. So I have here down the bottom left-hand side of the slide, this is a chronology of materials development. So it starts at the Stone Age, and it works its way all up to, its way through the rubber age, the polymer age, the composites age, which was in the 80s, and in around 2000s we started talking about functional materials, and now 2020 people are talking about molecular materials, and into the future it's quite obvious that the next branch of material science, the next wave of material science will be low carbon materials, so materials that are sustainable and that don't contribute to climate change. So we're looking at a sustainable future, a green future for material science, and that's the kind of work that I do in my group here at the University of Limerick. We work on these new low carbon based materials. So the resources of tomorrow in Europe are identified as follows. These are all waste materials, waste resources that we have in Europe that are not being valorized at the moment. And you can see on the right hand side, there's a list of building blocks that we can get from these waste resources. And we have identified lignin as a particularly useful building block. And lignin is currently, it's waste itself. It's not been valorized. There's a small portion used to produce electricity, about 2% of the lignin that is available. There's millions of tons of lignin available globally. Lignin comes from all sorts of plants. Mainly it comes from hardwoods and softwoods, but it can also come from miscanthus and other types of plants, as I said. And we use, for our work, we mainly use hardwood type lignins. Depending on the source, the structure of lignin can change, so it's quite variable. And people have in the past have said that this is a drawback, but we have found in our work that we can tailor the structure to different applications. So we have used this to our advantage. So this is kind of a summary of what we do. So the current kind of process for these materials are that there's trees. The trees get used to make paper. So the cellulose is taken out of the lignocellulose from the trees and is used to make paper. And then we have a byproduct, and the byproduct is lignin, and that's the waste material. So we use that waste material, we extrude it, and we produce a precursor fiber. It's a totally 100% bio-based precursor fiber, and we convert that bio-based precursor fiber into carbon fiber. And we not only do we use sustainable materials, but we also use sustainable processing. And the sustainable processing has led to a 75% reduction in energy usage and a 50% reduction in carbon emissions just from the conversion of the precursor material to the carbon fiber material. We've also used this in standard pan-based materials, which are the current precursors, or fossil, which are the current precursors for carbon fiber, and we found the same reductions with pan. And interestingly or disruptively, we've also noticed that the mechanical properties are retained after our processing, which is quite a significant result. So then as I said, we produce the carbon fibers, and we surface treat the carbon fibers, and we put those carbon fibers into matrix materials. We're now working with bio-based matrices, and we're working with recyclable materials as well, so recyclable composites. We're developing bio-based thermosets that are recyclable on demand. Up to now, there are some bio-based resins available on the market, but they're not 100% bio-based. They have the cross-linking part, the hardener part is still synthetic. We are using a new thiol-based chemistries to produce fully bio-based thermoset materials that are recyclable. And that's a current project that we're working on. So the idea is that we'll have a bio-based recyclable resin with bio-based carbon fibers within it. So for our carbon fibers, the targets are, the cost is like, we're looking at a 50% reduction in current carbon fiber costs. So we're talking about maybe €5 to €7 per kilo. Mechanical values, 2 to 3 gigapascals tensile strength, about 200 gigapascal moduli, which is pretty good, which is better than glass fiber for wind turbine blades. And carbon yields of greater than 35%. And we have produced demonstrator materials for wind turbine blades and for automotives. So why use lignin? Lignin, as you can see from looking at the structure, anybody that's familiar with carbon fiber production, you can see all those phenolic groups. You can see straight away that this is an ideal material for making carbon structures by just looking at the chemical structure, because these rings can fit together and make a really good crystalline structure and really good for carbon. And this is the most abundant naturally occurring aromatic molecule available to us. It's in fact, it's the second most abundant polymer behind cellulose. I'm just finishing up now, Paul. Just one sec. So it's so you might be wondering why have people not used lignin up to now? Well, that's because there's a low carbon yield, it's varying sources, and it's extremely difficult to process. And that's where we have, I guess, is where we've made our breakthroughs. So this is for people familiar with carbon fiber. You can see that this is the processing route that's used. Our main breakthroughs have been in the stabilization part, where we've been able to stabilize our materials faster to allow carbonization. So we've produced two types of carbon fibers. We produce porous fibers for functional materials, and we produce non-porous fibers for structural applications. So this is a scale up. This is the first scale up of carbon fibers that's ever been done. So we've scaled it up to pilot level. We've produced these demo parts. This is the first demo part that's ever been produced from a sustainable carbon fiber. So that's an automotive car wing plate. So that's the car wing for an automotive, and that's done in conjunction with Fiat. And we've also produced some infused epoxies matrices with air composites. This is some of the LCA results. You can see that there's obviously great benefits with regards to energy and carbon emissions. And the key development here is our mechanical properties. The state of the art is down here at 1 gigapascal and about 100 gigapascal modulus, 1 gigapascal tensile strength. Our materials developed here in Limerick are up here at 2 gigapascal, so twice the state of the art in terms of strength and stiffness. So that's it. Sorry for being a little over.
You're grand, Maurice. Thank you. I didn't give you credit. I was getting concerned. You got to 5 minutes and you still had half your slides. But
yeah, I got there.
No, great. It's great coverage. Thank you. We'll move on because I am conscious, very conscious of time. I want to get some discussion going. So our next speaker from the university sector is Yanis Milanakis, and he's at Sligo. So if you can share your screen, Yanis, that would be great.
Hopefully you can see my slides now.
Yeah, it looks great. Just check you can advance it, and then you're good to go. You're good to go, Yanis.
Okay. Great. Thank you very much, Paul. It's a great pleasure for me personally to be presenting in this meeting today. And also, of course, to see that the legacy of ICOMP, which has been all about the network, is being sustained and moved to the future, and credit to Paul and to UL for that. What I will try to do in the next 5 minutes is to give you a snapshot of our project, part of the SFI Plastics Challenge of this year, R-Square Epoxy, which is a collaborative effort between myself from IT Sligo, Angeliki Hantelli from the Varicomp group in UL, Marcus O'Connor from Udaras as Societal Impact Champion, and with the advisory presence of Paul and Andreas Heise from RCSI. Now, R-Square stands for Recyclable and Reprocessable Epoxy. And as you see there in the slide, part of this program is about identifying a challenge that relates obviously to plastic waste and the plastic waste management, go down to a specific problem and obviously speak about the possible impact that your solution might bring. In our case, our broad challenge has been the recycling of thermoset polymers and composites, which, as many people have already mentioned, it's not environmentally friendly altogether, and definitely you could not refer to it as being either mass or energy efficient. What we have discovered in these 4 months that the project is running is that overall there seems to be another issue that thermoset waste are not being really acknowledged. They're not being mentioned at all. That was quite striking for us. From this challenge, we selected as our specific problem to tackle the end-of-life treatment of epoxy composite wind turbine blades, and that's why this is relevant for today's discussion. And we have also identified a number of potential impact that we can bring from our solution, which I will refer to in the last slide later on. Now, it was quite striking for us to see that the whole discussion and situation around plastic waste resembles a little bit of an iceberg. All the discussion at the moment, and quite rightly so, is about thermoplastic waste, which are inherently recyclable, but we seem to have a very large component still submerged in a way of thermoset waste, which is definitely coming very strong, and we're going to have to tackle later on. A little bit more about the challenge and the problem. We have all seen all these very strong images of single-use plastics and the mountains of those being disposed in landfill and not reaching the appropriate recycling facilities. All these refer to thermoplastic polymers, which are inherently recyclable. Thermoset polymers, on the other hand, being irreversibly hardened, they cannot be recycled inherently, but they are, as we know, of equal widespread use and technological importance. We have already mentioned the difficulties with recycling of thermoset materials. And surprisingly, as I said, these don't seem to be acknowledged as a source of plastic waste. Many of the people here today are very well familiar and hands-on familiar in a way with the fact that thermoset composites are the ones that primarily replace heavier metal structures across a number of sectors, parts, and applications, with the very obvious benefits of reduced emissions and energy consumption. Amongst the thermoset matrices, of course, epoxy is a very well-known and a prime choice for wind turbine blades and marine vessel primary structures, for example. And as we have seen this morning, we have quite a lot of them out there in wind turbine blades, almost 2.5 million tons of composites currently in use globally. And previous speakers have referred to the life expectancy, which can be stretched to 30 years. So a lot of turbines are being decommissioned and a lot of new turbines are being installed onshore and offshore. Therefore, there is the question that begs what will happen to all the end-of-life blades and how will this affect the sector? And this has been already referred to quite a bit, and I can add an image, if you like, from a recent article in the Irish Times, and you can see the caption and the article title there, which are not, if you like, flattering for that matter. So this is indeed a problem that, in our view, requires some kind of solution. And our proposal in this direction has been that we can actually help in realizing recyclable epoxy composites, which can be cleavable on demand. And this we can achieve by synthesizing a range of suitable amine hardeners, cross-linker molecules, that already carry a pre-existing dynamic covalent bond in their structure. Now, I won't be able to give you the exact details of the structure today, but we should have a paper out soon, so that will be available for those that would be interested. Compared to, let's say, current solutions, we will try and we would endeavor to produce composites that are equivalent in both manufacturing and performance terms to their conventional currently available counterparts, but with the main difference that at the end of life, this could be recycled in terms of separating the matrix from the reinforcing fibers with an otherwise benign end-of-life treatment that again uses existing infrastructure that should be, of course, of benefit for the manufacturers. You can see our little proof of concept on the left-hand side there in the images. In the vial with the yellow powder is our novel epoxy hardener. That is, in essence, an aromatic amine that we have synthesized, and that's why it is being cured at a rather high temperature of 180 degrees. It can cure very well with the standard epoxy component, the Jiba, and give us a very nice looking there epoxy cured network. And most importantly, this network can actually be dissolved in an appropriate environment, which, as you see there, it's a combination of chloroform and methane sulfonic acid, so it is fairly acidic. That can happen at room temperature without any stirring, without any heating, so without any additional energy input. Now, the idea of incorporating a labile bond in the network to produce epoxy vitrimers is not a new one. It has been tried by other people, and there are a couple of, let's say, very well-known examples. We have the acetals, also known as recyclamines, that have been commercialized by Conora Technologies, which are already out there, and there is a large variety of them, but to our knowledge, acetals have an issue with acid resistance. They basically can be hydrolyzed in the presence of trace acid or even moisture. So that would be an issue with respect to the actual operation of the material. And of course, there is just one disulfide cross-linker that has been reported and has been used also in the project that also area composites are part. Just to finish off with a little bit of data for you, we can use our novel hardeners. They can be combined with the epoxy, and we can use different formulations and curing times. And as you see from the table and the TG values there, we can actually be very much competitive and on equal terms with both the conventional networks coming from standard aromatic hardeners as well as with the disulfide one. So we feel that we do have a good proof of concept with respect to equivalence in manufacturing as well as performance terms at this stage. Impacting in the event that this will actually go all the way and be commercialized, as you see here, which has been already covered by many of the previous speakers. And overall, we think that this is a good opportunity for us to, if you like, promote the idea of a recyclable epoxy composite and therefore a wind turbine blade. Now, that's me. Thank you very much for your time.
Thanks, Yanis. I think this is a very exciting early technology readiness level technology, and love to see it further develop. Hopefully you can get some discussion or interest from today.
Thank you.
With that, we'll move on. We've got Andrew Dixon from University College Dublin, UCD. Oh, we do not. The order has changed from my order. We've got Ian Major.
I don't mind, Ian, if you want to go ahead, you can.
I must admit, I was expecting Andrew. If we can, should we stick with the agenda I had? I think Andrew is next.
Yeah.
So if you could share your screen, Andrew, that would be great. And just put it onto slideshow mode and check you can advance.
Can you see that?
Yeah, great. Working perfectly. And it's advancing. You're good to go.
Lovely. Excellent.
Sorry, sure. Thank you.
Thanks, Paul. Right, so I'm Andrew Dixon. I'm a postdoc researcher and now a PI, and I've formerly worked in ICOMP as well, and currently working in UCD and the IFORM Manufacturing Research Center. And I'll be presenting some of the work as well from my colleagues, Professor Dowling, Professor Ivankovic, and Professor Cardiff, all of whom also were members of ICOMP. So when asking for slides, I was received about 60 slides to try and fit into 5 minutes. So I will give a very brief overview of kind of composite research, composite materials research in UCD, some of which is directly related to wind, some of which could potentially be applied to it, but we haven't gotten there yet. So if there's anything of interest at the end, you can email me and I can go into more detail. So there's three sort of major areas that we're going to look at, and first off would be materials tailoring. We've seen a few other presentations there on changing the material properties for recycling or for enhanced flexibility or for ease of manufacturing. We do a fair amount in that area as well, and I've broken those down. First of all, one of the most common areas that Professor Dowling has started looking at composites in was using plasma technologies to treat surfaces or apply coatings to composites. That can be used on metals as well, but it's quite heavily used in composites. And the idea here is that you use these plasmas to treat the surface, which increases the surface energy and allows for enhanced bonding properties. You can deposit coatings onto them for protecting them, like diamond-like coatings, diamond-like carbon. So that can be used in a wide range of applications. One of the areas Professor Ivankovic is quite adamant about is, and very well known for in the field, is nanomodification of composite materials. So this is a method of applying nanoparticles to alter the mechanical properties of a composite material. Just realized my camera's off. Sorry about that. So in other words, here what you can do is add various nanoparticles, such as carbon nanotubes. There would also be core shell rubber is a very popular one, as well as various short fibers. An example here on the right hand side is a carbon nanotube, and this is what the powder looks like essentially when it's bought. And by adding these in, carbon nanotubes in particular will increase stiffness values for the matrix materials. And then other particles such as the core shell rubber will increase the toughness of materials, but could decrease their stiffness. So by combining these different powders in different quantities, you can actually raise or lower various mechanical properties till you get to the point that you actually want in your final product. So that's very, very useful in this sector. Something which is actually ongoing here is the application of steel fibers into composites. And this would be combining these with a traditional carbon fiber composite, for example, has been tested quite extensively and was shown to increase the fracture toughness of a composite. In the middle here, you can see a DCB test being performed. And by adding just a few layers of this steel fiber into your carbon fiber composite, you can dramatically increase its toughness, so making it very, very resistant to impact in particular. So this is something that could potentially be applied into wind turbines for, say, bird strike protection and that sort of thing. Another area we look at is modeling and simulation. Everything from behavioral modeling, fracture prediction, up to topology optimization. Here's some examples from Professor Vankovic, modeling some core shell rubber particles within some epoxy. We also use it for optimizing the structures of composites. So say you don't want to use a traditional truss, you want to lighten it up or increase its stiffness, you can run it through various iterative programs until it increases whatever property that you desire, in this case, stiffness. And that also allows us to increase or improve the design of bonded joints and structures. So here, for example, we have a wind turbine blade. You can see the inner carbon spar and then the glass fiber outer shell. And essentially the point where these two meet is adhesively bonded in a lot of cases, unless it's co-cured. And we've been able to test various different laminate types and joint configurations, and then by combining those with modeling tools, we can actually determine their behavior before we make the first prototypes, which saves a lot of money. Destructive testing is expensive, particularly when you're looking at carbon fiber materials. Another area which is very active at the moment, particularly in the last 3 or 4 years, is additive manufacturing, and it was mentioned, I think, in 3 different presentations today. One of the areas that we look at the moment is the 3D printing of tooling and molding for composite manufacture. This example on the right hand side is just it's actually not one of our examples, but it just gives you an idea of the kinds of tools that we're looking at. So this would be a PEI or a PEEK mold printed on a large format printer, which we have several of here in the mechanical engineering department. And then you can use that to mold your traditional composite on top of, whether it's hand layup or ATP, and combining that then with other technologies which myself in particular developed during my PhD several years ago. We're able to print the mold and then use a additive manufacturing type of system mounted onto a 6-axis robot, and we're able to print relatively complex curves directly onto the mold, and means that if we want to do 1 or 5 parts, we can do very low cost, short run batches of these parts. And if we then want to scale up to mass production, we can go and make the molds the old fashioned way with steel or aluminium, whatever we want. The very last area then that we look at a lot is composite 3D printing. And this would be printing the composite itself directly in a machine. So as William said from NUIG earlier, the Mark Forge system we would have used for the last 5 or 6 years. And this was used in conjunction with NUIG and ICOMP to print these carbon fiber insoles. And at the back there, you can see this lead coming out of the carbon fiber. And essentially that was a force sensor that was embedded into the part as it was printed. And we were able to put these onto a person, and as they walked, it recorded data from the stresses applied to that point in the composite. So there's a lot of different ranges of application for this kind of technology. Currently we're looking for any interested parties actually for a commercialization project which started in January, and next year is a trial year, so we are looking to trial this kind of technology. We're 3D printing composite components. We have something there as well, which is like an example of a small composite bracket. And I'm sure we can have a brief discussion if interested after this presentation, but that's me finished up.
Thanks, Andrew. Yeah, good overview. Thank you. Yeah, anyone who wants to follow up on those aspects at the end can contact Andrew directly or in the chat later. Now, moving on to AIT, Athlone Institute of Technology. Ian, are you there? Ian Major?
I'm here, Paul.
Thanks. If you could share your screen, that'd be great. Yeah, we can see that. Slideshow mode, and just check you can advance the slide.
Yep.
Perfect. Thanks, Ian. The floor is all yours.
Okay, folks. I'm from AIT, part from the Materials Research Institute in AIT. So this is probably one of my last presentations as being from AIT, as we're on the verge of merging with LIT to form a technological university, which should happen in the near future, we think, or I think. So AIT, we're probably known more for plastics research. So we've been the home of sort of plastics research and plastics education in Ireland for close to 50 years. So we do all, in terms of research, we do all things related to polymer processing and sort of polymer design and polymer testing. So we take companies through the design stage, prototyping, manufacturing, and then testing things. So we have a processing arm and a testing arm, as well as our design team. We do different small-scale projects, innovation voucher projects, up to multi-year projects with national companies, international companies. So for composites research, we're focused mainly on thermoplastics. I'd say we're probably 80-20 in terms of 80% of us is thermoplastics, and now we have a growing interest in thermosets. And we've invested in bringing in external expertise and hiring people that are very capable in the thermoset resin development research. So our main flagship and what came out of ICOMP and sort of Enterprise Ireland funding was our pilot line thermoplastic composite production line, which is capable of processing the very high-end peaks up to 450 degrees C resins down to polyethylene and a whole host of materials in between that. So we can, on the line, we can process small batches, less than a kilo, up to 15 kilos an hour. We can make granules for secondary processing, such as injection molding, over molding. We can make 3D filaments or 3D printing filaments for standard fused filament fabrication. And then we can have different melt-coated fibers, short fibers, that's anything below 5 millimeters, long fibers, that's usually anything below 25 millimeters, and continuous fiber. And we have the ability to process a host of fibers, glass fibers, carbon, as well as Kevlar, and our cutting line is capable of cutting Kevlar. So in addition to this pilot line, we also have our injection molding, over molding facilities, 3D printing, melt spinning for making fibers to make yarns that we co-mingle, and then working with partners such as Axis Composites in Northern Ireland, we can make weaves. We do compression molding, and then we have a suite of mechanical and thermal analysis testing. Related to the wind turbine, and as part of our own philosophy of enabling zero waste plastic, we have a range of technologies, and we have our sustainability platform, which contains our bio-ICEP EU-China flagship project funded through Horizon 2020. And we're looking at different processes to recycle plastics into usable, break the plastics down back into monomers, and then we polymerize the monomers back into thermoplastics. So we are interested in household waste, plastic packaging, and of course, what fits into that is the waste turbine blade materials. And how do we break down the cross-linked thermoset resin as opposed to the thermoplastic resins? So we're using a range of technologies, biochemicals. So Margaret and her team are using enzymes to help pretty much eat plastics, convert the plastics, break them down, turn them into monomers, which then we can polymerize. And we've got a lot of different other technologies. So when it comes to wind energy sector, our interests, probably one of our main interests is the recycling. So turning that wind turbine blade waste back into monomer building blocks. In terms of production facilities, Thomas mentioned the Twintex material. We have the capabilities of making our own Twintex type materials, using melt spinning and co-mingling to make the yarns that then can be woven into fabric that you can turn into the smaller thermoplastic turbine blades. Of course, we can alter all the thermoplastic resins that go into those materials, so with a lot of flexibility in what we can do. And of course, we have our weathering and testing facilities that can help industries such as the wind energy. That's my contact details. And then also Declan, who's I think on the call here, Noel Gately, who runs our technology gateway. Okay, thank you.
Great, Ian, thank you so much. This brings us to the final speaker in the session. I'm aware we are running late, and apologies for that. I hope you agree that the presentations and the content makes it worthwhile. We will continue with the Q&A after Paul Butler's talk. Paul was our contact and representative for Enterprise Ireland when we had the close relationship with ICOMP, and Paul was sort of instrumental and in nudging us to continue with the ICOMP network. I think that's a nice way of putting it. So it's great to have your support. Great to have you online, Paul, and hopefully you're going to give us an overview of Enterprise Ireland activities in the space and how we might be able to apply for some funding.
Absolutely, and thank you very much, Paul, for organising this. I noticed in some of the early presentations, Chris Harrington mentioned about Earth Day, which is tomorrow. And of course, a lot of what we're doing today is all about trying to reduce the Earth's damaging load that humanity is bringing on itself, or wrath on it, essentially on it. But I want to just put my presentation here, so I'm going to just transfer you now. Hopefully, you will see this there, and
see that. Yeah,
good stuff, and hopefully you will see that. Okay, great.
Perfect.
Good stuff. So yes, thank you very much for everybody, and thank you for staying on so long for all of you. I know it's been a long day. I won't be very long. Hopefully, I won't be. I'll try to keep it within certainly the 10 minutes, and maybe even reduce it a little bit more. But just to say that Enterprise Ireland supports innovation in the composite sector, and we will continue to do so. We're very much in favour of this continuation and the activity that's going on. And so my presentation today is really around to customers, to companies, pardon me, and to researchers in third level as well. And so just to give you an idea of the importance of innovation when it comes to working with industry. and third levels. Those very companies that do involve themselves in innovation, tend to separate themselves out very much so from companies that do not involve themselves in innovation. And you can see, and this is quite an old slide here, but it shows the significant gap there is there in terms of capability of companies that do involve themselves in innovation, and that very much involves not just what happens on site within companies, but also with third level institutes as well. So I'm going to talk to you today about a couple of different types of supports that we provide. The first one that those people within third level who are on the call will be familiar with, hopefully, is the commercialization fund, and this is really around supporting researchers to do what they to research what we believe is applied research activity, ultimately something that would be lending on to forming a company or a license, a spin out, whatever. So essentially it's designed specifically to so one of the very first ones of that, and there's a number of different ones on the commercialization fund, is a feasibility that we'd like people to go through, and this is really around validation of the commercial opportunity and looking at the IP space, looking at the market itself. It's an access to grant where you get a consultant to go out, look at the opportunities associated with your idea, and come back hopefully with a positive response from the marketplace. If it's not positive from the marketplace, life is short, move on. And I'm sure there are going to be other activities and other research subjects that you could spend time on. So we would recommend that anybody who wants to go after commercialization fund does a feasibility first of all, and it certainly does a lot of de-risking in terms of its potential funding thereafter. So that leads me on to the commercialization fund. And it really this is designed, as I said earlier on there, to develop, build and validate the technology from both technically and commercially. The significant funding is available there, and typically, we'd be talking about €250,000 per project, and these would be typically over a 2 to 3 year period. And there are some people on the call who have taken advantage of this form of funding in the past. Okay, I'm going to go on to move on now to innovation partnership funding, and this is funding that is primarily focused at companies working with third level institutes, and it starts with an innovation voucher, and this is we give these away like confetti, to be quite honest with you. And it really is kind of a door opener for companies who haven't really done any activity or haven't worked with the universities and institutes of technology in the past. It's €5,000. It can be an additional €5,000 thereafter, and there's also a co-funded €5,000. So you get three kind of bites of the cherry here on this in bringing your idea forward. And in some cases that leads to an innovation partnership. Initially, what we like people to do probably is a feasibility, and this is a little bit different in some ways to the feasibility that you'd associate with the commercialization fund. It's primarily around again de-risking the technology, if you like, kind of a short-term study that would be done by the principal investigator to develop the proposal for a full innovation partnership application. So there's a kind of an element of suck it and see around this. Okay, so that's what the feasibility is primarily around. And then you've got your innovation partnerships then as well, which is the main one. And depending on the size of the company, if it's industrial collaborative research or experimental collaborative development, you can get a grant rate of between 40 and 80%, and there are rules associated with that. It's very easy to find out information on this because you can go and Google innovation partnership and it'll pop up there. So, okay, in summary, what I have here is 5 different types of funding mechanisms that researchers can go after, either on their own or with a company. The commercialization fund feasibility, which is valued at 15,000, which is really around the marketplace. The comp fund itself is typically around €250,000 over a 2 year period. And it's about applied research. Innovation vouchers, which I said we give away like confetti, and this value in and around the 5,000 mark that companies come to the university or the IT with. The innovation partnership feasibility at 9,000, where you're de-risking the technologies, and then innovation partnership again working with the companies and third level researchers working together to look at a solution. I say typically 80,000 there. In fact, I've seen consortiums coming in under innovation partnerships with projects at the value in excess of $500,000. So it's not new. So that's it. That's from me. Thank you very much indeed.
That's great, Paul. I mean, you said everything. First of all, I just want to thank you for your support over the years and current support, and to Enterprise Ireland. There's still plenty of opportunities for us to work together, which you've outlined.
Absolutely.
And what I'm hoping is to expand that from not just Enterprise Ireland Forum, but actually other types of funding. We have no limits on what we can apply for. So hence the international element of today. We want to partner, we want to reach, we want to make connections, both on the island, in the south, across to the north, as well as our friends and neighbours elsewhere in Europe and beyond. Yes. So with that, I'll take a little pause for breath. I know we are running late, and I apologise for that. But I do want to get some Q&A sessions, so if you can hang around, please do. I understand if you cannot. This is the formal time to end. And Paul did a Herculean job to get us in on time. But I do want to get some questions going. And I know the chat function isn't working, so please raise your hand, and you can voice it by muting yourself when you're selected to do so. Alternatively, you can put it in an email to me at paul.weaver@ul.ie. Anyway, we have got a question. I've had an email come to me, and that's directed to Clodagh and Harold, and it's about some of the materials being used. So perhaps Clodagh can go first. The question comes from Walter Stanley at Limerick, and he's asking, have you investigated the employment of recyclable infusible thermoplastic resins, such as CBT or Elium liquid acrylic, or indeed recycled PET fibres and matrix, which are truly, so it's PET fibres and matrix, which are truly cradle to cradle in terms of their recyclability? Clodagh, would you be able to go first?
Yeah, no problem. I had hoped that Paddy was going to direct all the questions, considering I did all the talking, but that's okay.
Well, actually, between the two of you, I didn't mean to victimise you, Clodagh. Yeah, Paddy's getting all the credit. He needs to do some work, doesn't he?
No. We haven't, I suppose, in short, we haven't actually looked at this, but we would be interested if such a route was available, and it would make this a lot cleaner for us. So yeah, we'll have a look into that. Thank you very much.
Okay, great. Harold, I know it's getting late in the day, but thank you for still being here. Good to see you. You want me to repeat the question, or are you okay?
No, I just come with the answer. So to the first material, no, it was not evaluated. Well, it was looked into the cyclic polyesters as a start material, but cyclic polyesters, they do not fit into our process very well. Elium was considered an alternative. We are right now not working on it because we put our focus on other technologies. But yes, it has been identified as an attractive candidate for future, maybe.
Oh, that's interesting. Walter, did you want to come back on that? You can unmute yourself if you wish.
Thanks, Paul. Thanks for fielding that. No, I've been looking into this for a long time, nearly as old as your beard now at this stage. But no, I got some encouragement. My internet is coming and going, so I didn't quite hear all of the answers. But I do see that some of the Arkema Elium resins have shown some promise, and as we say that they are thermoplastic and potentially rethermoformable, so they can be essentially recycled, reused or repurposed. And the whole PET thing, I think, is inherently green and cradle to grave to cradle again. So that's just my area. So thanks, Paul, for taken that question and posing it to.
You may not have heard, but Harold actually, they are looking into helium, so he said it was of interest.
Oh, great.
Maybe you can contact Harold directly on the PET fibers and matrix, and we can hook you up with contact details afterwards if you so wish.
Cheers, mate.
No, okay, no problem. Please, any other questions? I'm going to go to my email, but please raise your hand. Questions or comments?
I have a question there, Paul. It's Paul Butler here, and it's a question primarily for the maybe Siemens or maybe even John McCann, or even Claude may know something a little bit about this as well, or some of the researchers. And it's really around looking at the end of life aspects of blades. You know, has there been any work done on retesting, recoating, and redeploying those blades?
Okay, I think that was directed to ESB, Clodo or Paddy. Is that right, Paul?
Or Siemens, even.
Okay.
Yeah.
Maybe, well, Harold, you go first this time, maybe.
Yep. So this is done as well. So we do also some health monitoring of the blades, and if possible, they will also be used for some further applications. So some of the blades that are taken down in repowering projects here in Europe, they are then sent to Africa and applied there again. So yes, this is done to avoid decommissioning right away, to use it in some countries that would not have the same amount of money available for huge projects.
Yeah, and I can come in on behalf of ESB there as well. We're currently, our particular wind farms are coming up to that 20-year life. So therefore, we're looking at extending the life of those, should it make financial sense. And I suppose that's when we'll have to balance the books with regards to how much money we need to plow in to do that, that refurbishment, if you like, of the blades. I was also very interested, and I missed the name, apologies, of the presenter who talked about the blade replacement and the technologies that might be available there. So we're currently weighing up how much input and how much money that we need to actually put into these particular projects, extending the life of them, and whether or not it makes financial sense. I note that in Germany, the average life cycle of the turbines is actually 16 years. So they redevelop each wind farm in a much shorter time frame than we have.
Well, Clodo, I think I can connect you just before I'll come back to you in a second, Harold. Thanks for putting your hand up. I think the person you may have been thinking, what I remember was Thomas Flanagan from Aero Composites was talking about blade replacements.
Yes.
So hopefully, if Tomas is still online, he can come in now, and then I'll come back to Harold.
Yeah, no, it is something we're really interested in. I think you reach the fatigue life on blades, or they've only been designed with kind of a 20-year life in mind, so they get extended to 25, but beyond that, people are not really sure. But like, we're really interested in all of it. We're interested in reblading as well, because I think the challenge for us would be to make like an 80-meter blade is probably beyond an Irish SME, I think, at this stage anyway, unless we had an awful lot of money. But to do sort of a 25-meter blade for reblading, we could do something like that. So yeah.
Now, hopefully, there could be some scope from some basic research in there with the university sector. I mean, can you see either of you opportunities for that, Clodo or Tomas?
Well, the reblading stuff we've been looking at with SEAI, we've actually got a proposal in for blading. It's under evaluation at the moment, so hopefully that will go well.
Very good.
Yeah. Yeah, I don't know. There's just loads of opportunities. Like, I think the stuff with helium as well. We haven't done anything with it, but we're aware of it and we're interested in it. The whole, like, there was a lot of talks about recycling, and I think that is, it's a massive opportunity, but it's really difficult. I mean, it's just, and I actually think there's also design for end of life as well, that even if we make the current blades in a better way, that they can be broken up at the end of their lives. It's not something we're looking at enough.
Well, I agree with that. We've got projects under consideration for design for disassembly at the end of life.
Yeah,
I think.
Yeah, absolutely. And I think I'm heartened to see that Harold talks about finding new new markets and that sort of thing in Africa. But one of the things we have to be very careful of is that we're not dumping blades in Africa.
Harold, Paul, let Harold come back in there because I interrupted him anyway. So Harold's still there. Maybe there's a couple of things you want to come back in on now, Harold.
Yeah, it's actually only one comment on the repowering, because it turned out that the lifetime in Germany, as mentioned, with the 16 years, it has mainly something to do with the huge steps that have been done in the development of new technologies in turbines and blades. So commercially, it would make sense for some of the project owners to replace their turbines much earlier than the actual lifetime of the whole turbine. So if these turbines would then be reused in another country or maybe third world country, they still get a very good product there. So it's not like just having the waste disappear. And for sure, if we ourselves as a company sell these turbines to another country, we should also take the responsibility for the waste.
Yes, good stuff. Thanks, Harold.
Very good. Next question is one actually if you here, Paul Butler. Somebody asking about the equity implications of an EI grant. Does EI take a stake in the IP, and if so, how does that work?
Generally, no, we don't. No, what we do is the grant is to the university or the IT. If there's a spin out, normally the institute looks for some sort of equity in the spin out company. And that's negotiable. So that's something that can be quite desirable sometimes for a newer company anyway. It gives it some credibility as it enters into the fray of the big bad world.
Yeah, I think that's a very clear answer. Yeah. So basically, no, it's altruistic actually in that sense. Just wants to get wealth creation, get some business going, isn't it?
Correct. Yeah.
More questions, please. Raise your hand or put them in the email to me, paul.weaver@ul.ie. Or if anyone wants to start a discussion on any particular aspect, please raise your hand.
Hey, Paul, can you hear me there?
Yeah, please fire away.
Yeah, so just for those that don't know me, my name's Greg Clancy, researcher in the University of Limerick, and just a question that I probably more have for Claude as an operator of wind turbines. Is the end of life of a turbine blade just mainly decided on its age? That is there any kind of, like you mentioned a lot there, 16 years, 20 years, 25 years. Is there any testing done on the blade to see, is it still in good use? Is there any damage? Because in the last few years, the level of non-destructive testing, or let's say the scale of it, has improved a good amount. That is there kind of scope for having a large non-destructive testing kind of like completed on the blade to see that has it been damaged or has it been fatigued over the years? Is it still suitable for use?
That's a very good question. And as I said, we haven't necessarily done any of that within the ESB. However, we are starting to talk with the OEMs in terms of what they may have done with existing wind farms of the same age and the same type, which may have been just a little bit older than our own turbines. Our oldest wind farm is 2003, so that's just coming up on that. So one of the things that we're looking at is the cost of those refurbishments. And for the likes of some of our turbines sites where we only have one or two or maybe 4 or 5 or 8 small turbines, whether or not it's worth repowering and putting on larger turbines if we don't have the site for it. It might not necessarily make sense to repower, but certainly the lifetime extension may make sense for those. And then when we look at some of our other wind farms where we're talking about maybe 70 turbines and a much larger land mass, we may be looking at, it might not be value to refurbish all of those turbines. We may just get more bang for our buck by actually putting on bigger turbines on those sites. So that's part of the project that's going on at the moment. And I know we've started talking to OEMs on a number of those smaller projects just to see how much that's going to cost or even the feasibility of it.
That answer your question, Garode?
Yeah, no, that's perfect. I think it just seems interesting that the end of life could be just based on years. So, John, if you want to come in there,
I can add to that let's say it's a significant research challenge, and there is a new IA Wind task set up on life extension of wind turbines, which is mainly concerned with assessing the remaining useful life and the methods to assess remaining useful life, which would include various forms of inspection and testing. But the target of that task would be to produce a recommended practice that would eventually be adopted as an industry standard. But certainly we're open to anyone who's interested in participating in that task in applying in their next call.
Yeah, that's perfect, John. Thanks very much. That answers my question perfectly. Yeah.
So, Claude, I think you had your hand up anyway. Or am I mistaken?
I did actually, but I suppose it's more, I don't know if it's a question that really John McCann from SEAI can answer. One of the things that drives our development of wind farms is obviously based on our tariffs and whether or not a developer can make money from something like that. And then again, it's going back to the lifetime extension versus a repowering. If what we have we hold, but where those tariffs might necessarily fall away. Just wondering if John has any information on whether or not there's going to be a tariff for doing a lifetime extension where we can't necessarily increase the output by 50%.
I don't have any information on it, but it's unlikely. I suppose where it's according to what falls within the definition of repowering. I suppose repowering currently targets under RES 50% output is targeted. So endeavoring to qualify where it's not where there isn't a major investment, it's unlikely to be subject to continued support. That government would consider that the market revenues should be sufficient to keep existing assets running.
Okay.
But it may not justify an investment case. I suppose that's the challenge. So, and it may be, I suppose, more exploration of what repowering means, because repowering can mean different things to different entities.
Exactly, and maybe it is a blade replacement might get you over the line with some of them.
Yeah, certainly a blade replacement is a fairly significant capital exercise.
Yeah, indeed. And then I had a second question for Chris Harrington of the Castletownbere Harringtons. Would that be Castletownbere itself, or maybe a bit more west to Allihies and Scrivogue, in which case I'm one of your long lost cousins?
No, we're the heart of Castletownbere, so close enough.
Okay, no, that's fine. At one stage, my great grandfather was a Harrington, and he happened to marry the only Harrington that they were not related to. So I happen to be related to any Harrington west of Castletownbere.
Yeah, that sounds like the Harringtons.
Oh, well, I said with this seminar was about making connections, didn't I? That's an unexpected one. Thanks, Clodagh. Thanks, Chris. Oh, I see a certain Paul Weaver's raised his hand. He wants to ask a question. So it's really one for the blade manufacturers. So Harold and Tomas. I think for design for end of life is easier in thermoplastics, and we need to get the economy of thermoplastic composites down, the cost of them down. New materials, maybe the basic materials are already there, maybe not from replenishable suppliers, but imagine we had some cheaper thermoplastic tape. And I'm thinking then for sort of AFP, automatic fiber placement, automatic tape placement. Do either of you have an idea of the sort of a cost per kilo of a finished product of that material, which then starts to make it competitive. I know this is business competition for you, but ballpark figures would be helpful. Maybe Harold can go first.
That is a quick one because I don't know. I really don't know it.
Okay.
It's too many people involved in these things, and that's so far out. I don't blend into any procurement stuff.
Yeah, well, I think you're pretty wise, and I appreciate your candor as well. What about you, Tomas?
It's a bit the same. Like, I don't want to say a figure that would be wrong, and like it's very easy to be wrong. But I can say a couple of things. I think it has potential. It's actually part of the Merwind project we're looking at. Not so much the cost, but look, it's the deposition rates. So you need to lay down like tons of this stuff, like very quickly. And there is issues then about crystallinity and the problems that introduces. But also the shapes are not as complex as some of the things you'd be working on, Paul. So you could possibly put down really thick tapes if they existed. So I think it's where things have to go. I think it was Harold, I'm not sure, but someone was showing just how manual the process still is for laying up materials. So for glass blades, I don't think you'd use ATP because, and I think you're talking about €3 a kilo, that kind of a price for it, and that's almost fabricated. Roughly, I think you're €25 a kilo on the ATP for carbon, but I wouldn't really stand over that, but to throw a ballpark out there.
I mean, I had my own ideas, but actually you're reinforcing what I was thinking. I mean, you never know about, I'm not in business, am I? But yeah, that's what reinforces my own ideas. Just for you, Thomas, we're launching a PhD looking at this specific thing, sort of ATP materials and deposition rates for wind turbine blades. So we should get in touch about it, actually. I think it may be of interest to you.
Well, I just had one comment relating to some of the other stuff about reblading. There's a bit of, it's sort of John alluded to it. In between repowering and reblading, there may be something about reblading without making the turbine bigger, so that you put more efficient blades on older turbines. And the appeal of that is that you can do it quickly, whereas like anything for 2030 targets, there isn't much time to get there. If you have to go through a 5-year planning cycle, you're just not going to be able to do it quickly. Whereas if you can kind of upgrade your existing turbines, there can be a business case for that. So we think there might be something in that as well.
I can actually answer the, sorry, chairs broke. I can jump in there. We actually did quite a lot of work that from my Bristol days on retrofitting existing towers and infrastructure with new longer blades. It's those longer blades, as John inferred earlier, is actually lowers the cost of energy. And these are aeroelastically tailored ones, so they can they basically cut through the wind in a more efficient way.
Just from a developer's perspective, I suppose, to bring it back to that, as I'm getting beaten by the sun here, the problem with longer, more efficient blades is the planning process, and they are essentially different to what we sought planning permission for. And so therefore you do have to get back into the planning process to do something that's materially different. That's why I was quite interested in the fact that, reblading like with like, and yet being able to get more out of it. That's a very interesting concept.
I must admit, I slightly don't get it then. I thought the refitting of blades, they won't be the same. I mean, they're going to have to be. How can you get more if they're the same diameter?
Well, just the blades will be designed a little bit more to get more energy out of it, so there'll be less drag.
Or for the same length. Okay, so maybe better aerofoil shapes. Maybe less maintenance. I can see from that perspective, with better materials, perhaps.
That's certainly what I took away from that presentation.
Most of the energy, the LCOEs mainly, in my understanding, is mainly going to be driven by the length of the blade. So the advantage of retro would be to put some slightly longer blade. But then you see that you've just made it completely. I wasn't aware. Then that affects the whole planning scenario. So
it does, yeah. They're effectively, the tip height is bigger, so we've got shadow flicker issues and noise issues, and yeah, it's essentially a material difference.
You'll let John come back in a bit before you do.
Yeah, I suppose
got his hand up, and we'll come.
The material aspect of it, or it has been carried out. There are examples of it having been carried out in Italy. Was where I'm aware of it having actually been implemented, and the performance improvements were a mixture of the aerodynamics, but a couple of meters increase on the blades as well. Now, it wasn't a very substantial increase in the blade diameter, but it could be considered material because, let's say, wind farms are subject to such intense scrutiny these days.
Yeah.
But yeah, you would still. I think the example that I was aware of brought something like a 20 to 25% improvement in annual energy yield, with let's say a small increase in blade diameter, but it was from a combination of both improved aerodynamics, reduced loads on the turbine as well because of the lighter blade, and that increase in swept area.
John, I guess the analogy for the planning side is building an extension to your house. You've got to work within the planning rules and within a certain, maybe small volume extra or meterage extra, then you don't have to get the planning permission. So if there is a small extension, Clodagh, maybe it doesn't have to go through planning.
I'll have to talk to my planner on that, but I think he takes a very conservative view on this. Just interesting, John, if you could recall that wind farm and maybe send it on through Paul, that would, or my details might be.
Yeah, I
great.
There was a report on the internet a few years ago about it. I'll see where I've saved that to.
Clodagh, it's ETA 4X, ETA number 4X. If you look that up, that'll take you to where you want to go.
Thank you. And I suppose just on the planning isn't necessarily, just for those maybe haven't been involved in this, planning doesn't necessarily have to be just the envelope of the structure that you're building. It's also, we really do need to consider the environmental impacts. And so if you're bringing your blades closer to the ground, we have to consider the ornithological impacts. And I know Paddy would definitely be bringing that up because that's really his area of expertise as well. So we need to make sure that we're not actually impacting any of the ground nesting birds as well. Unfortunately, it's a little bit more complicated, and I'd love to be able to just stick on new blades and get more out of it.
Yeah, good comment. I've got a couple of other questions. I am conscious of time. I think discussion's been really good, by the way. I think we were making connections and actually pointers for future research as well for the composites community. Mohammed Rui, you have a question? If you do, please unmute yourself.
Yeah, thank you, Paul. Actually, I had one. Maybe I'm not sure from who I should ask this question, or it's a comment, or even it's a question or not. It was just an idea. I was wondering, has anybody ever heard about this idea of the transportation of the wind turbine blades? That has anybody been doing that or thinking about that in near future or something? That these large big blades can be transported via a group of bespoke or general drones, just to alleviate the problems associated with transportation on land. So just for the sake of curiosity, maybe it's an idea for future, for composites, for transportation of that, to make some drones for transporting large wind turbine blades.
I'm happy to come in on that, or if there's somebody else that might want to come in on that as well that has experience.
Go away. Yeah, carry on. Sorry.
Oh, go away.
I meant go away as in go talking away, but then I realised what I said. Sorry, Clodagh.
We considered it initially in ONNE because we were looking at 56-meter blades, and that particular chicane in the last photograph in my presentation, we were to the wire. I think we made millimeters in it, and that was it. And removal and reinstatement of that structure, which was essentially a very old asbestos shed, was not considered in our planning permission, and therefore we had to navigate our way through that with millimeters to spare. And when we were looking at it, we had to say, okay, well, if we can't get this through, what will we do? And we considered not quite a blimp, but trying to helicopter them in. The economics of it didn't make sense because it was we were dealing with a lot of different turbines and therefore a lot of different blades. But we did consider it, and I think depending on what's going to happen in the future, it can actually happen. But there's other ways of transporting. China uses blades generally come in a flatbed truck. China uses a clamp system such that the blade can be put vertical, the truck can be shortened up, and then you can get past the chicane or whatever you need to do, and then come back down again and elongate the thing.
Yeah,
so,
I've seen that. Yeah.
Yeah, transport companies can do very, very clever things.
Yeah, nice, thank you.
In my language, that would be a morphing truck. The truck is changing its shape to do something, perhaps. That's kind of it. Well, I know it won't be. It'll be some sort of cherry picker, or large cherry picker, or craneage or something. But that's an interesting solution. Now, Will, you have a question or comment?
Yeah, I've comment and a question. And they're both for Clodagh. The first is we've actually put in a project. Tomas has mentioned it a little bit, Reblade, as part of the latest SEAI call. But Robert Farrell from ESB is a collaborator on it, so you're part of that project. So if it gets through, we might have something in that sphere to work with. And the other thing is one of the projects that I mentioned earlier, and Tomas mentioned as well at the end of his, it's a tidal energy project, but we're looking at using recycled composites for their foils. And is that using more recycled materials? Is that anything that's on your radar at the moment, or?
I am not aware of it, but that doesn't necessarily mean that it's not ongoing.
Okay. Yeah, no, that was just a wondering if you were interested in that sort of area as well. Might make them a little more, the end of life would be a bit more friendly for your blades then.
Yeah.
That's it. Thanks, Laura.
Yeah, no problem. You're fine there. Paul Butler, you've got your hand up.
Yeah, thank you very much. Yeah, it's I suppose it's a question. It's really around blades themselves and about manufacturing of blades here. And I know this is a volume business ultimately, and shipping blades around the world has become quite efficient. But I have a discussion with a German company on Thursday, and it's really primarily around Germany's hydrogen plans and strategy. And there is an interest certainly on the west coast of Ireland, and what can be done off the west coast and can be harnessed from the west coast in relation to hydrogen. And I know that Clodagh has been talking about some hydrogen generation there, probably on the Moneypoint site. Claude, any thoughts on that? Or even John McCann might have some ideas on it as well. You know, what sort of volume would we need to get to before we could potentially attract in a large blade manufacturer to the island of Ireland?
It might be one actually for Jerry Hallisey as well as John McCann. Unfortunately, Harold's had to leave. It's 6 o'clock where he is. And he sent me a lovely email, and I said, yeah, just slip away for the moment. And I thanked him for his fine contribution today.
Very good.
Maybe can I just maybe suggest Jerry goes first, and then maybe John?
Yeah, we've had a great question, Paul. We've had a couple of conversations with a couple of the big players in this realm, and the general consensus of opinion is a 2 gigawatt pipeline per annum would justify a manufacturing facility in the estuary. Now, that's a 2 gigawatt that would be various blade sizes, because it could take onshore wind into account, but also the blade requirements that would be there for the Atlantic resource. But it's in that realm of, and once you get into that size, you're looking at 100 turbines a year. So that's what, 300 blades. But that's certainly on the cards, and how quickly we could ramp to that position. But as part of our efforts here to bring forward the timeline on delivery of the Atlantic resources, we're calling it. We're looking at all aspects, hence why taking out large, and I appreciate there's been a lot of conversation about LCOE there, but the large component parts of it, from our point of view, would be the vessel infrastructure that would be required for assembly and such like, and that's why the quayside infrastructure and bringing any or as much of the manufacturing element to the estuary as possible takes out the large component parts, which are the vessels to a large extent, and the availability. So we are working on that, and the figure now, whether it can be lowered, is what we're trying to do, and bring it in at its earliest potential. Obviously, we're not going to get to 2 gigawatts straight away, but I think the potential is growing, and how quickly we can get to that is going to be, and maybe there's a ramp-up scenario there as well. So, yeah. But the interest is there, and it is something that I think, even from Paul's point of view, from an undergraduate, postgraduate point of view, it would be a terrific resource to have manufacturing on a large scale, a large commercial scale in the estuary. That's not taking away from Tomas and what he's doing up in Galway. And I'd hope to actually, I wasn't aware of that, and hope following on from this to have a conversation with him about his aspirations in this regard.
Yeah, I'll just very briefly add to that. Brilliant, Jerry. I'll just say add to that. The scale that could be there, Paul, would mean that you need your workforce, and not just, you can't just bring the workforce in. You've got to develop it. So that goes hand in hand with education, research. We have to develop our own IP long term, as well as actually bringing in the designs already and manufacturing locally. You can't it's not economical sense to transport blades too far from where they're going to be deployed. The issue would be, I guess, is that the population of Ireland for outward investment isn't so great, so we have to look how they can export. How are we going to export energy, which we read, because Ireland can be self-sufficient. Once we know how to store and transport the energy that comes, then the future is very bright. John,
part of that route to market proposal there, and the bringing forward of the timeline on potential blade manufacturing, or any other component for that part, is the hydrogen proposal, or derivatives of hydrogen, be that ammonia or others, and the international vessel refueling in the estuary, and the export potential. We've had a number of conversations with nation states about their lack of facilities to facilitate their own requirements in those derivative fuel markets. So the potential for Ireland to export from our shores into their realm is extremely high, and there's a huge potential in that regard. So the sooner we can get most of this moving, the sooner we can optimize the potential for, and we're constantly for Ireland Inc.
Well, this is why I thought ESB Equinor investment, I mean, is so important, because it's, once people see things starting to happen, then things can snowball.
Well, that's one of only 4 at the moment. There's 4 developers. They haven't all made their intent known publicly yet, but they've had conversations with us. So I think the total of the ESB Equinor aspiration presently, and I hope it would expand from that, was in the region of 1.5 gigawatt, but we're currently looking at 6.4 gigawatt off the Clare coast, which is, it may not all come to fruition, but I think the more we can show the ambition, and that's what I said earlier in the presentation, it's about not thinking small. Let's think big about what we can do and what we can bring here, even in the short term, because the advantages are tremendous. And to Paul's point there, just a little earlier, that's part of what we're doing in our engagement with the universities for a working group as part of that, to make sure that there is that capture. You don't all just bring in. And part of that, of course, is the likes of floating foundations. I mean, that's not all graduates and undergraduates or postgraduates. There's a lot of without sounding demeaning, lesser education requirements for some of the roles that would be required in that scenario. But there's also, we have to have the complete pipeline and the workforce to do all facets of of what's required.
That's great, Jerry. I was flagging a bit because we're going on for a little while, but I'm re-energized again after listening.
I suppose just to get back to previous conversations we've had with manufacturers for onshore turbines would have indicated that they'd require several hundred megawatts per year to make it worthwhile. Now, because the offshore turbines are so much larger, it may bring it up to gigawatts. Now, it is difficult to keep let's say a gigawatt supply chain going year on year. The other thing I would suggest that is, looking at some of the required innovations, is that if you string some of those together, you may bring about a radical change within the industry. Let's say innovations that lead to on-site manufacturing, for example, and let's say projects that might bring several of the innovations like recyclability, manufacturing techniques could place Ireland in a position of advantage where it's currently disadvantaged.
Well, I love that thought, because that's what we want to aspire to, is game-changing technology and find the right people to partner with for exploitation. And the game-changing technology, then the whole world looks up to what you're doing. So
and the other thing I would say is that wind energy is a huge global sector. Ireland, however big it becomes here, will still be a relatively small player, and exploiting a niche market globally can have much higher value than dominating our local market, for a large component. So, and those niches, we should be chasing after them as well, and that could be as much providing design services or various services in the supply chain without actually manufacturing. So there are plenty of opportunities there.
Yeah, we are doing some of that already. I know, yeah, but I see the potential there for some place like Foynes, in fact, to supply to the west coast, but also around to the east coast as well, because it'll have a deep harbour there, and something could come out of that. Plus, also, I feel that we talk about infrastructure as well. There has to be a major infrastructural investment at a European level, and I'm going to go back now to the good old days of the supposed or the proposed European highway for electrons, essentially going down the west coast of Ireland as part of the European supergrid, and all these DC lines that were proposed to go in. But I think that all of that potentially is still there in terms of ideas, and at a European level, I mean, if we are going to get even the whole hydrogen thing getting going as well, we're going to see a lot more electrons need to be moved around, but green electrons for green hydrogen,
Well, without speaking on their behalf, Paul, I think it's a very interesting one. Supernode and Eddie O'Connor, especially with their connectivity with Acre Solutions in Norway, are proposing for that European supergrid, and it gives a connectivity on a route to market, especially for an outlying area like the west coast of Ireland. And if you take the overall position that EirGrid were taking as part of the consultation, where they didn't see a major input from floating offshore wind on the west coast until well into the next decade, which I think the ESB Equinor announcement there from last week certainly threw the spanner in the works there, in that the ESB, and again, not looking to speak for anybody, announced that they expected to have a contribution there for 2028. I think when you start looking at that, I think talking to Supernode as I am on a regular basis, they're looking that their technology and the transmission lines could potentially be in place early into the 30s now, which gives another tremendous route to market, and that potential obviously is greater when you're talking electricity rather than a 2/3 of the resource, as Eddie O'Connor says when he talks about hydrogen. You're only getting 2/3 of the potential when you're dealing with hydrogen, rather than the 100% of using electricity into a European supergrid.
So I think, guys, this is great discussion. Connections been made. We're moving away from composites, and I'm also conscious of the time. Composites of the time, conscious of the time. So I think I just want to invite anyone who has not asked a question, because we've had if they've got any comments or questions, and then I would like to bring the event to a close. I'll have a few closing comments before we do that. But is any final comments or questions, preferably from somebody who hasn't yet had opportunity to do so? Okay, I'm just looking at my email. There's no more messages in my email. Okay, well, I think it's been a fantastic event. It's longer than we planned for, and I apologise for that. But I think the content's been superb. I should be, that's my perspective, but I guess I have a vested interest. So we had a stellar cast of speakers today, and I thought we covered everything from the basic materials development right to the operation side of things. So from that, I think it's been really successful. I want to invite the ICOMP community to basically, we're going to give a survey around and see if you thought this event worked and what we can do better. We know there's some obvious things with IT and timing we can do better. But whether this thematic-based event whereby we look at what the opportunities are for composites by industry is a good thing to do. And with that, as part of the survey, we'll be asking you to say what theme we should have next time. Maybe it even has to be something zooming in on some specific aspects of wind energy, maybe on materials, manufacturing or design, or tidal energy, or it could be a different sector. It could be agriculture. There's possibly huge possibilities for composites in lightweighting agriculture in Ireland, for example. It could be space activities. I'll leave that for you. It could be biomedical. So we're going to pass around a survey and look for suggestions. If anyone's got any now, just before we close up, please raise your hand, and that will be foremost in the consciousness if you put that in now. Any particular sector you would like to see us have a thematic workshop on next time? Okay.
Composites and transport, I think, is going to be really important for the future. It's certainly an area that needs a good look at again, because there's constant development in that space.
Which form of transport, Paul?
All types, quite honestly. And I'm talking about, sorry, land-based. I'm talking about here.
Okay, yeah. So I mean, okay, land-based transport. Yeah, I can see that.
Yeah.
I was going to suggest automotive, but it escaped my mind.
It could include agriculture, is what I'm saying, really. So
yeah, very good.
You know.
Yeah, very good. Okay, I think we should wrap it up there. So this has been recorded. We will make it available. This is an open forum. We want to make connections. If you've got any comments or questions that crop up after you've seen the presentations again or later on, just email us on the ICOMP Network email address, which is being made available. It's actually on the agenda. And if I don't hear from you in the short term, I look forward to our next event and speak to you soon. Enjoy the rest of your day, everybody. And with that, we'll close the seminar for the day. Thank you.
Thank you.
Thanks, everybody.
Thank you.
Thanks to all the speakers.
Thanks, Paul. Thanks, Paul. Thanks, everyone.
Thanks, Paul. Bye.
Thank you.
Bye.